My name is Sergey Plis, or Dr. Plis for short, if you will. And I'm a professor, associate professor at Georgia State University, and director of machine learning core at the Tri-Institutional Center of Neuroimaging and Data Science that combines Georgia State, Georgia Tech, and Emory universities. And today, I will tell you in this talk about research that I do, that my group does, and that I do with all of my collaborators. Some of them are on the slides. And hopefully, I will convince you that it's very interesting direction, and I will also explain what are the problems, where are we going, and what are the further challenges. But mainly, my work and the work of my group is focused on machine learning and brain imaging. And it is kind of a circular uh, setup when machine learning is feeding on brain imaging and brain imaging is benefiting from machine learning. The goal is to improve brain imaging and to improve, in general, healthcare related, outcome related methods, and also learn from the brain, learn from the diseased brain, and invent new machine learning that is helpful beyond the brain imaging. And uh, yeah, let's. In this talk, I will cover first motivation, why we're doing what we're doing, where we ultimately going with all of that. And then I will talk about brain semantic segmentation methods and also challenges that we still have to resolve. Then I talk about the most important question of all science, causal learning, is how to uncover the mechanisms and some results in complex time series modeling from my group. And decentralized learning as well, because yes, we're working with the most powerful deep learning models, but they're data hungry. How do we get data for deep learning when the data is not Twitter scale data sets, which are immense, but they're meaningless. In a sense, they're cheap, while medical data is very expensive. Two versions. First, a romantic version. And here's a nice demo from from the internet that I link in my slides that you can get to. The basic idea is by looking at this demo, you can appreciate how vast our universe is, and even our solar system is just unimaginably large. If this pixel, a single pixel on the screen, is Moon, and you see the scale, and we start with the sun. If we want to waste this whole talk waiting, by going with speed of light from the sun towards the first planet, we can spend a lot of time. And I can just sit back, enjoy, and relax, watching emptiness and reading these smart comments in in the corner right here. But let's not do that. Let's just say that we'll get to Earth in about 8 minutes if we travel with the speed of light. To the Getting to the outer planets will take us, again, if we travel with the speed of light, lots and lots of time. And well, if we go to random direction from the sun, then we risk not hitting any planets at all. In this large solar system, there are only little speckles of dust or of planets. But imagine traveling further and further away. The motivation, or maybe basically my personal conclusion, is that the universe is so large And the physics as we know it now doesn't allow us to travel instantly anywhere. So our bodies, our species, are not built for this. It's just too boring, frankly, to just wait most of the time, or like 99.999% of the time. But we can't not explore. We can't not go outwards because every time we stop, we fall. So we must build machines that will do this for us. But machines cannot just be sent to other planets and start be pre-programmed or start exploring and learning on the side. First, they need to arrive to the place, absorb the information just by observing, make plans about experiments because the conditions on those planets and beyond even the solar system, they will not be um, the same or similar as we can pre-program. So those machines will necessarily have to learn, and they will necessarily have to learn first from observation and then from experimentation. But just from experimentation is too expensive. Say modern reinforcement learning is just taking too many trial and errors, and well, even if we have an ideal reinforcement learner or a reinforcement learner closer to human performance, still even us, we don't act immediately and we don't learn just from acting. We first observe, learn, and then make models and then act. So that's a romantic view of that motivates us, that motivates my work and motivates the work of my group. But there is also a pragmatic version, a pragmatic view, and pragmatic version is also a little bit romantic, I guess, because we want to understand the disorders in the brain, and the brain is the most complex system that is known, arguably, but I would argue that it is the most complex system known to us, to humankind. And it's interesting to understand the brain from two points of view. One point of view is, of course, improve quality of life of our species. Mental disorders are so debilitating and put a large toll on our society. But another point of view is if we can learn how the brain works, even a little bit, we can use this knowledge and that information into building better algorithms, better machine learning system or artificial intelligence, if you want. Um, and we can learn a lot from differences between healthy brain or control brain and brain with diseases and disorders. It's very hard to study brain, or it used to be very hard to study brain without getting inside of people's heads. And if we get inside of people's heads, that cannot be done deliberately. It's either if there is a medical condition when we have to crack open it, or uh, I guess, or we can't. And Only relatively recently we gain ability to study human brain as it functions, and that's thanks to brain imaging. So we using brain imaging for disorder understanding. Well, doctors and researchers, psychologists, neurologists, uh, that's a very useful tool. But once we get a useful tool that physicists or physics in large gives us, that allows us to look inside of the human brain into the action of human brain and structure on human brain function and structure. Um, we want more, right? We want more data, we want more fine-grained data, and we work together in concert with physicists and with engineers, and we develop methods that go to cellular level, to millimeter level, to sub-millimeter level, and further down, and we collect data at finest resolution, thinking that the more data we have, the better we understand. But unfortunately, more data is just the start of understanding. It's not the end. And high dimensional data is not easy to see through. It is a problem. The more data we have, the harder it is for us to extract the relevant knowledge from the data. We need, or the dream actually, we want to collect more data because we righteously think that the information and the knowledge is hidden in the data. And it's like when we collect less data, we're not finding out as much, or we will not learn as much, even theoretically. But once we have a lot of data, it's like, okay, this is a mountain of data. How can we learn anything from it now? Um, well, the dream is that algorithms, AI, robots will be able to look through this data and point us to important information, help us to make discoveries. So the developments that are needed for that are synergistic and comparable with those that are needed for space exploration eventually. So here's where those two romantic and pragmatic view converge. We need better algorithms for machine learning, and we need better learning algorithms that can learn something useful from large amounts of data. And let's start before going into space. Let's start from the most complex system known to man is human brain. Before we continue, let's have a 5 minute course or even shorter. Everything you need to know about neuroimaging for this talk in 5 minutes or less. So definitions, right? Neuroimaging studies brain function, produces immense amount of data. Data comes in various forms, each with their strengths and weaknesses. And our goal, or the goal of neuroimaging, is to understand how the brain works and breaks. Functional MRI. Well, let's first look at the structural MRI. What you see here is structural MRI, or a slice. When an MRI is collected, what we effectively get as a result, after a lot of pre-processing, but let's ignore that now, we get a cube that consists of small subcubes with uniform gray level value in each subcube. So here, this picture consists of pixels, but because it's just a single slice from somewhere here, if the head is hidden over here, this is the back side, the occipital, the ears, and everything. So MRI, or structural MRI, is static, just a cube of gray level voxels. Voxel is a three-dimensional pixel. Functional MRI measures the brain's function via blood oxygenation level dependent response, BALD response, and it produces four-dimensional data. It's a three-dimensional volume changing in time in this fourth volume. Strength of fMRI is that it's relatively well localized. You pretty much know exactly where the signal is coming from. The weaknesses, it has slow sampling rate. It used to be every 2 seconds, now it's every half a second. We can do that with some loss of accuracy, but we continue to increase the sampling rate, and this weakness of slow sampling rate eventually disappears. But the problem with functional MRI is not just the rate, if you recover the rate, but the smoothness and the sluggishness of the bold response create a problem in detecting um, what was causing it in time. So there is a sort of a temporal inverse problem when it's very hard to figure out what's going on because the signal, even if you sample it at high resolution, is very smooth, low frequency signal. Another modality is magnetoencephalography, measures magnetic field outside the brain, also non-invasive, and it has its own strength, instant reflection of underlying activity. The moment your neurons fire, or the moment large amounts of neurons fire, sensors, superconductive interference devices, those squids on the picture schematically represented as blue pellets, they detect the signal immediately, but the weakness is uncertain spatial location because all of our sensors are outside, and uh, we know starting from Helmholtz times that if we try to localize what inside of the head caused the measurements that we get on the sensors, we are in trouble because there are multiple solutions. The problem is ill-posed. And even though with some careful regularization we can solve it to good accuracy and good spatial resolution, still, it's not as certain as fMRI. Yet, the cause, the root cause of both of the signals that we're collecting, magnetoencephalography and fMRI, is the same, neural activity. On the picture is, on the picture over there is a pyramidal neuron that is causing MEG activity. That's what we're measuring, dendritic currents in pyramidal neurons. But fMRI, still, it is the brain activity. We measure absolutely different uh, phenomena. As I said, it's blood oxygenation level response, BALD response, but it's not that we're measuring a completely different cause of the signal. And a little construction that will let us understand one section later in the talk is Bayesian network. Bayesian network is a way to carefully exploit sparsities in our joint probability distribution, sparsities in the conditional independence structure. When we can decompose joint distribution as a product of um, conditionals or families. Like here, a family has a child and two parents. So probability of hippocampus depends on amygdala and hypothalamus, and that's uh, that's a family in Bayesian network. Uh, Depending on how we train those networks or how we infer them from the data, we can even assign causal semantics to this data, and then they're called causal networks. Semantic segmentation. What are we trying to do there? So our task is we have a cube of the brain, MRI, static cube. Every voxel is just gray level. That's what we see right here on the left, right? Different slices of the brain. So this is a T1 image. Yes, this is a T1 image, and our task is to segment just the brain. So we have everything. We almost have the face and all irrelevant pieces But our task is to segment the brain into gray matter, which is red on the screen, and white matter, which is yellow. And uh, various ways to do that. Okay, another task is a little bit akin to modern day phrenology, but now about regions of the brain, and it has much more solid footing than the actual phrenology of the past. So we know that neurons in the brain form groups that specialize in certain function. Visually, unlike just gray matter and white matter, they don't look differently, but we know that um, as denoted by colors here, those regions, the neurons or the voxels in those regions that represent the neurons, they go together and perform certain function. When we decompose a brain into those sections, it's called an atlas. So now we have a full atlas of the brain. We know what each function, each functional piece, functional regions of interest does. The problem, the difficulty is that we want to do that within the space of each individual brain, each subject space, and in this space, there are roughly no, very few correspondences because our brains are like fingerprints. They're very different, and they're determined by our prior, well, it's everything ontogeny and phylogeny. Uh, the point is, can we process the T1 cubes images and mark specifically for the subject where those regions are in the brain? Yes, we know we can through titanic effort of people at Massachusetts General Hospital. We have a tool called Free Surfer, multiple electrical engineering, signal processing, pattern recognition, and other tricks, and we can go from MRI image cube to segmentation of that image first, and then to surfaces that are also segmented according to the atlas. Nice tool, very complex, very complicated. Used to be that it would take around 30, more than 30 hours per single brain to do all of this processing. Right now, it's around 8 to 10 hours, depending on the hardware. So, if we want to apply this tool to large scale data, so our machine learning can benefit from this data, like say 30,000 subjects, each takes 10 hours. That's too many hours to wait and work with it. So, can we automate that by using end-to-end learning in deep learning? So standard way to automate semantic segmentation is UNet. Um, UNet is introduced by Ronneberger and then extended, introduced in 15 and extended in 2016. UNet heavily uses skip connections and um, down convolutions and up convolutions because it has a structure of down convolutions and then up convolutions that are connected with skip connection, but just mainly because of this structure, the U shape, it's called UNet, and an interesting model, fully connected model. After it was published in 2015, it became extremely popular, especially in biomedical segmentation, for the segmentation. The problem with this model is that it has very, very, very many parameters. And jumping a little bit ahead of myself to one of the sections of this talk, if we want to train this model across the sites such that in a collaborative manner, in decentralized manner, then it's around 2 gigs of parameters or 2 gigs per gradient exchange if we want to train this model in a distributed fashion. So, a nice model. Uh, but Alex Fedorov here on the picture um, came up with a different idea and implemented, tested, and made it to work. We call it MeshNet. It doesn't have skip connections. It's basically all layers of the same sides, some kind of like you can envision it as a pipe. Nothing changes, and it doesn't have any fully connected layers or anything. Input a MRI cube and get a segmentation at the end. The trick is, or the difference is that we're using dilated convolutions in those layers. So you can see there's green rectangles here represent dilated convolutions, and dilated convolutions do not add parameters. They have the same number of parameters, but can exponentially increase the field of view um, of the network. So one point to note is that in traditional CNN, when your receptive field stays the same, in order to see from each layer above, to see larger and larger field of view, you need exponentially deep network in order to see larger field of view. So you need very many layers. In dilated convolution, because of this dilation or opening up of receptive field, you can preserve the number of parameters, but open up and capture the field of view much faster. If you think about it, what happens when you apply a dilated filter to your data, it is similar to applying a SHA function to your time series data in Fourier transform. So the more dilated is your filter, the less it's capable of capturing high frequency. But importantly, for brain segmentation, we don't need to see everything in focus and high frequency. The small fovea, the small field of view for this network will be in high frequency. That's where we will, or the network rather will, because it's an end-to-end process, will segment and assign label to the voxels, but it needs to see the full brain completely, even though blurrily, because in this blurred vision, it's still visible. Are you in the front of the brain, in the back of the brain, left or right? Because the semantic segmentation of the brain depends on where you are, not on the tissue type. So it can segment gray and white matter. Another trick that Alex used there is, okay, you have 60,000 voxels or even more in this cube, in MRI cube. And for a human to go through each of them and label them even in 3 classes, not brain, gray matter, white matter, is tedious, not too many data set that are human labeled. So we used free surfer, which computationally intensive but state of the art. So there are lots of data pre-segmented already available. So we used FreeSurfer to train our MeshNet model. And interestingly, and we'll see later in this talk, that FreeSurfer is not ideal. FreeSurfer makes mistakes, but FreeSurfer makes most of those mistakes in a sort of non-systematic fashion. And as we'll see, that MeshNet learns to generalize beyond these mistakes. So the teacher is artificial. It's like a simulation, like learning from a simulation or simulator. But the network gets to be really good. And another advantage for an application in the following section of this talk is decentralized learning. Compared 23 million parameters with 72,000 parameters. of MeshNet, 23 million for 23.5 million for UNet, and 72,000 for MeshNet. 600 kilobytes versus 2 gigabytes. Well, this is for a model that is simple and only segments gray matter from white matter. Um, it becomes a little larger, maybe around a megabyte or two. But besides being able to compactly train that model across the websites, this is highly shareable model. You can just attach the full model to an email and send it to another research center and continue collaboration. So the process is like that. Neither UNet nor MeshNet can feed the whole MRI volume and pass it through all of the activation layers. The network or the badges will not fit in even in the V100 32 gigs um, network GPU cards. So what we do, we carefully chop the brain into small regions, and we do it by sampling two-dimensional, three-dimensional Gaussian that is centered around the central mass of the head. And then after the network is trained, the way we predict, make prediction is by ensembling all of the predictions from all of the overlapping uh, volumes. So that's the process. And here's the result. Quite good. Free surfer on the left, the data in the middle, and MeshNet on the right. Um, so here are examples where free surfer kind of merges cerebellar structures, the fine grained structure, why MeshNet is a little better. And then free surfer lost a lot of gray matter over here. And this is unseen data. MeshNet was not trained on that data. Okay, that's visible. So free surfer lost gray matter over here, and MeshNet captured that. Then corpus callosum wasn't captured by free surfer. Something went wrong. Look, corpus callosum. So interesting, non-systematic error. Deep learning model can generalize beyond the teacher. Although there are mistakes on the MeshNet side as well, capturing some skull, which we don't need, or um, uh, sparser segmentation, sparser than needed, and a little bit of skull again over here. So, but the interesting part is that MeshNet can be better than human, and all those models actually can be better than human in those complicated tasks. Imagine how a human does the labeling. First of all, three modalities come together, and based on all of three, which are three-dimensional, each of them, human must look in all of the cross sections and label, decide which voxel is which. But it's tedious and virtually impossible. So I'm judging just by this example, but it looks like what a human has done. They were looking at the slices one by one, and they didn't notice that in this slice they messed up. Everything kind of merged together, whereas the MeshNet again captured corpus callosum quite nicely. And biometrics on the gray matter and white matter, it also does better than UNet. So what we got here, an easy segmentation, semantic segmentation model. It's compact and portable, send it via mail. Universal and adaptable, as we just saw. And of course, the code is available, and it's also implemented. The code is in PyTorch, but if you were a fan of Keras and TensorFlow, you can Google no-brainer package that contains the MeshNet model. So what's next? What are the challenges? Will Ashby is working on the next step. Free Surfer does not just do segmentation of the brain voxels. It also takes the voxels and creates a fine-grained surface. It's imagined as if going from a voxel space, coarse resolution grid into almost infinitely smooth. There is a non-parametric representation. Well, in free surfer case, free surfer generates parametric representation, and this represents difficulties for us when this is an input to a network, whatever the black box network is, and the network returns an output exactly in the same space. That's one thing. But when an input space is those voxels in 3D or however you want to structure your input, and the output surface alone, just for one hemisphere, contains 300,000 or close to 300,000 vertices. That's a challenging story. But if we can generate from MRI the surfaces, we can up the game of tools like FreeSurfer, and we can augment FreeSurfer and make it a faster tool and hopefully better because speed usually transfers in something great because we can do more runs, more optimizations, uh, other interesting sort. Arguably, the goal of all science is to uncover the causal mechanisms of the systems at question. In this small section, I want to highlight the work that my group has done and is doing in causal learning. And you see the pictures of my collaborators and former lab members. They all contributed to this section. Well, actually, they've done most of the work. So the question is about multimodal causal learning, where no fMRI is slow but spatially focused and spatially precise. MEG is not so spatially precise but temporally really fast, so dynamically capable and rich. Can we infer causal structure of fMRI? Um, Causal structure of brain regions, how they interact from fMRI and from MEG separately without dealing in creating physical models of combining them, which we also have tried. You can write me, I will point to a paper. Can we combine those modalities? So Rob Tillman um, has tried, well, David Danks and Rob Tillman and uh, Peter Spiritus and others at Carnegie Mellon University have developed methods, IOD and ION, that allow us to join two causal structures learned from different experiments with just overlapping variables. So in our case, MEG and fMRI are only capturing some brain regions that are the same. MEG is having trouble capturing brain regions that are deep in the brain. fMRI sort of captures everything, but again at questionable temporal resolution. So there is already a method. There was a method back before this research was started that could merge those causal structures and create a joint structure that is more informative than simple net sum of the causal connections of those two causal structures. Well, but for imaging and fMRI, we don't even know if they're compatible. I published a paper back in 2011, where basically with the causal structures, what I've shown that if you focus same subjects, same task, everything the same, only data is different. And if you only look within the MEG data and versus if you only look within the fMRI data, the conclusions that you will arrive to are orthogonal, completely opposite. So clearly, both of those modalities, both of those data sets, they're telling you the same thing about the underlying phenomenon, or the underlying process is the same. But if you only worked with imaging, then you would conclude that complexity of the underlying network increases from condition A to condition B, targets and novels, and fMRI goes the other way. That's not good. That means that we need to work with all available sources of data and combine it constructively so we learn more. Uh, but the problem with imaging and fMRI is this different sampling rate. So, say we don't know what is the true causal sampling rate, but we have a causal time scale and measurement time scale. Measurement time scale for MEG is around 100 milliseconds, and measurement time scale for fMRI still predominantly around 2 seconds. So what causal inferences can be made when measurement time scale and causal time scale are not the same? And two challenges, right? When we started, and notice we work with multivariate time series data. Multivariate time series data is well studied, at least in econometrics. If vector autoregressive model, ARIMA, ARMA, SVAR, VAR, lots of interesting research. And when you analyze those models, you still, being a scientist, you need to be thinking causal interpretation of this model. And no matter how many times you say correlation is not causation, we don't care that much about correlation. We do want to infer causation. So the problem was largely ignored because it's very hard to deal with, very challenging when you deal with it parametrically. And in this line of research, what we did, we approached the problem non-parametrically. And one problem is forward inference. What happens when our measurement time scale becomes slower or rougher than our actual causal time scale? So that's forward inference. And backward inference is, okay, well, my physical instrument is sampling slow. Can I infer from the causal graph that I estimated from my slowly sampled data? Can I inform what was the true graph that generated this data and generated this graph? That's backward inference. So let's address both of them quickly here just to whet your appetite. Forward problem. Let's make a few assumptions. Causally sufficient model. There are no exogenous common causes. There are no unobserved common causes that affect more than one variable. And then we assume first order Markov, that we can always go to a time scale fast enough that there are no connections like that, because no signal propagates with infinite speed. We can assume that there is a time scale or for this particular system where it's first order Markov. And then for the same reason, no isochronal edges. We're sampling fast enough. Nothing is happening with beyond that reach within the slices, at the same time slices. So that's our dynamic Bayesian network model. Stationarity assumption, stationarity not of the signal, but of the causal structure. With the same causal structure, we can still generate a lot of interesting signal. And when you unroll your Bayesian network, because it's Markov order 1 assumption, those windows are all the same. That's the Assumption of what happens in undersampling effect. Assume that at true causal time scale, you have this particular structure of dynamic Bayesian network. If you do not observe every second sample, notice how structure changes. The important thing to pay attention to is that this new structure is not wrong. It is statistically true to your data. That's what your data tells you. If you don't know that you didn't observe this uh, samples, that you undersampled by two, every second sample was dropped, every second observation of all of your variables was dropped, then your structure changes. And then the more you undersample, the more your structure changes. Can we deal with it somehow? What's going on? How to even reason about problem like that? What we came up with is a way of representing Markov order one model as a compressed graph. And a compressed graph, couple of theorems aside, we know that no matter how you're undersampled, Markov order will stay the same and isochronal edges will not appear. Only bidirected edges will appear, may appear. So in compressed graph, we take a GBN, we take a GBN representation. 1, 2, 3, 4, 1, 2, 3, 4. And we're saying, okay, 1 causes 1, and 1 causes 2, 4 causes 1, 3 causes 4, and 2 causes 3. So we take this representation and fold it into compressed graph representation. Now it becomes very easy to deal with, and you can actually develop methods and develop an intuition and understanding what happens when we undersample by one, isochronal edge appears. So instead of one, we undersample by one. So one, instead of going to two, goes to two and then to three. Oh, okay. One to three. And then two, instead of going to three, goes to two and three. We don't observe the three. That's how this new structure forms. And the same three, instead of going to four, it goes to one. 4 goes to 1 and then again goes to 1. Okay, it stays here, but it goes to 1 and goes to 2. So this edge appear and this don't exist, and that's what we get here. But we also get isochronal 1 and 2 edge because we don't observe the 1 at the previous time step, and we have an unexplained correlation there. Okay. That's clear. So what we figured out that if you consider those graphs and run strongly connected component decomposition of the graph, then we can look at strongly connected components of the graph of those graphs separately, and the simple loops or the lengths of the simple loops, greatest common divisors of the simple loops, determine what will happen when you undersample. So that's interesting. And if greatest common divisor is 1, then one thing is happening. If it's not 1, another thing is happening. So take a graph, decompose it in four or all of its simple loops, make a set of the length of the simple loop, and compute the greatest common divisor. Few things, specific behavior. If you had a DAG, or if your compressed graph was a DAG, that's different from directed acyclic graphs. That's different from having a DAG in DBN. This is now only about compressed graph. So a DAG can only, as you undersample, can only drop all of the, lose all of the edges. So you observe and declare that everything is independent in the system, but it's not. It's actually like there is interaction, there is causal system acting there, but because it's a DAG, you won't see anything we will notice, or at best you notice unexplained correlations. Another is superclick. If your GCD, greatest common divisor of simple loops, is actually 1, then as you undersample, you will get all possible edges. The graph just becomes densely connected. All of the possible connections are there. And an interesting behavior, if greatest common divisor is not 1, then you get an oscillating behavior depending on how you undersample, your nodes can become, or random variables can be observed as independent, or say this is a ring connection, or causal structure could totally flip, and then it'll repeat, and then again flip, and back and forth, back and forth. So interesting. So now let's solve the backward problem, inverse problem. Remember again, we've collected the data, looked at the data, estimated the graph, but the researcher has a reason to believe that they're not sampling at the correct rate. Can we give candidates to researcher candidate graphs that could have generated what they see, and then they can use their background knowledge, their prior knowledge, and filter that out. So we have used some theorems that we've proven and developed an algorithm that is basically a constrained satisfaction or branch and bound pruning algorithm um, that uses those theorems or this little lemma that I showed. But ignore that. The main point is that we went through multiple iterations and improved our algorithm in the following way. We started with a baseline algorithm, and then we reduced the number of candidates that the algorithm considers by 30 orders of magnitude. We need 30 orders of magnitude fewer steps or fewer explorations in our algorithms. What it meant is that our original solution at worst would take 8 hours, 25 minutes for a simple 8-node graph. And once we solved all of the problems and obtained this algorithm that works when we know by how much we undersampled, 316 millisecond, huge, huge savings. And we can deal with large enough graphs or like 20 variable graphs, and other samplings up to 3 and 4. But what happens in unknown undersampling rate when we the ideal case here is you collect the data and you know nothing about it besides that it's not at the correct sampling rate. Can we generate all possible candidates at all possible undersampling rates that could have generated this graph? Just showing you that it's all, don't try to parse what's there, but with a theorem and a corollary, we devised an algorithm called rate agnostic structure learning RASL algorithm that acts and functions quite differently from mesochronal structured learning MMSL algorithm for known undersampling rate. And again, fit this picture there just as illustration. I will tell you everything you need to know. It's very difficult to dive into little detail in overview talk as this one. But we figured out how to return all of the possible candidates by specifically structure our problem of sweeping through all of the possible graphs and carefully pruning in time. The only problem is this algorithm is very slow because now you simultaneously considering all the undersampling rates and all of the candidates. It's very clever, very efficient, um, but we hardly can work with random variables beyond 10. It's just hard. Still, there are lots of scientifically interesting systems where 10 variables is more than enough, but beyond 10, it's difficult. Well, and then we met our colleagues and our friends, and they told us or taught us about answer set programming, its constraint satisfaction approach to constraint satisfaction problems, and for example, problems and NP-complete problems such as 3-SAT and more, and basically for mesochronal structured learning from for MSL algorithm with known undersampling rate, you can compare our code in Python on GitHub and this complete implementation. And a spoiler, this code in Python is much longer and much more complicated than those lines. Uh, and while the answer set programming, which is realized by Lingo tool in Pataska system from developed in Potsdam. What it does, so computation time in milliseconds for all various densities of a graph of a fixed size. Look what happens. Answer set programming, satisfiability solver. The time almost doesn't get affected. This is a log scale. Complexity of MSL algorithm grows exponentially. So at certain point after 100 seconds, we just stop. We just capped there. So, but now let's see how many variables algorithms can handle. As you see, MSL tops around 35 variables in the graph, but solver, the satisfiability solver answer set programming in Klinga can go as high as 70 variables within an hour pretty easily. That's impressive. Well, not all of them complete, but okay, I'm ready to wait overnight. How many will you solve? Will you go to 100? Probably. Yeah, that's a powerful approach. So, interesting finding, interesting solutions, but we haven't solved everything yet. So how would we handle graphs with multiple strongly connected components? We only solve all of those algorithms are about a single strongly connected component of a graph. But then another task is, okay, MSL, mesochronal structured learning, when converted to answer set programming settings, became super powerful compared to its previous incarnation. But we don't know what to do about Razzle because we don't know how to codify Razzle's assumption in answer set programming, and Razzle's still there. It's the most powerful algorithm that we currently have because it can give an answer candidates at all sampling possible undersampling rates without knowing the undersampling rate in advance. But the problem is it's very inefficient. Just 10 variables is our limit. So it would be nice to improve efficiency. Another challenge is, okay, we have developed another theory. It's one thing to take complex time series data and undersample. Don't observe particular um, time intervals. But another thing is totally fail to measure a random variable. What happens to the graph? So we know the forward process, we know what happens to this graph, and we can codify it or, with data structures. But now we need to write algorithms that can go from the measurements back to those latent variables. And then yet another question is where we started from. Why are we doing all of that? Well, we want to bring causal structures of MEG or any other faster modality and causal structure of fMRI, slow modalities together to the same baseline so we can do fusion of their graphs and learn more about brain structure, causal structure of the brain. I have complex models that perform very well, and I don't have time in this talk to cover all of them or any of them in the depths. But as you may know from your other experience with working in deep learning with deep learning models, or if you haven't worked with deep learning models yourself, you may have heard that they're data hungry. How do we get more data and train deep learning models? So one, and especially in research and biomedical context, so one standard approach is data sharing. Let's share all of the data, and then this sharing of the data will improve effective sample size. Um, Diversity of the data will become, our samples will become more representative, and that in turn will improve generalization of our models. But if we share the data, how do we solve the problem of motivation? I spent many months writing this grant proposal, and then I spent many years collecting this data. Why would I share my data? And then ethical and legal issues. Okay, well, if the subjects trusted me and um, came and participated in my research study, that doesn't mean I can give their data away to anyone. And plus, did they sign a consent form that allows that or not? Oh, yeah, I didn't think about it at the time. I forgot. So the consent form of a subject doesn't contain the clause that allows sharing the data, and so there's a lot of data laying around that I would love, like the researchers would love to participate in uh, research activity, further secondary research and findings, but they can't. It's just there at the hard drives. So, and also the trust, and it's again ethical issues and the trust are connected. If my subjects trust me and they participate in my studies, how can I just give away their data? And then technical administrative issues. Of course, everything is possible if it's regulated, and we hire a lot of lawyers that do a lot of difficult work, um, playing with all of the possibilities and trying to um, arrange them on the paper of what could happen and what can't happen. But then it takes a lot of time, a lot of effort. And okay, I just want to quickly share the data and answer a quick hypothesis, and then I'll know, do I want to spend years on analyzing the data, not or not. That, but even doing that, sometimes I can, and I need to wait, or researchers need to wait a month or two or three, sometimes years, to get a permission. So to fight that or to help avoid those problems and augment those situations where data sharing is actually possible, we've created a framework, platform called CoinStack that allows people run computation on virtually pooled data in a privacy preserving manner. We what we did, and it's all available on GitHub. It's all open source. You install a tool on your local machine. Don't talk to IT. It's just too complicated. We work by port 80 HTTP port, and you already met people that you want to work with. That you all running our coin stack, joining into a consortium. Computation is running in such a way that local data is analyzed locally. No data is sharing. Only some statistics travels around between the nodes, and in the end we get an answer as if our data was locally was all pulled together, and we have analyzed it all together. We have multiple methods implemented in the settings, multiple approaches, and one of the approaches is differential privacy. Well, some of the approaches are differentially private, some are not, and differential privacy is this whole paradigm of how to ensure privacy of the data. So we've devised something that like how to train differentially private classifier and how to correctly aggregate it such that the error is reduced. And it was later extended by Google people, and the extended version is very well known. It's called Pate. So what happens is what we do, we have 11 hospitals or 11 sites that want to train a classifier that classifies healthy controls and schizophrenia patients from the volume of the gray matter in their brains. Each of them can't share anything about their subjects, about their patients, and they want to guarantee the privacy. So what they do, they create differentially private classifier. Each of them trains a differentially private classifier, and differentially private classifier adds a little noise, or sometimes a lot of noise, um, using the method of objective perturbation here to the output of the classifier to the predictions. So what we have here, we have a largish error, 25% or around for all of them. So yes, they are safe. They can put their classifier online, but their classifier is not as useful. So what we suggest and devise the schema is 11th side, the aggregator takes all of those classifiers, applies them to the data, and trains another differentially private or plausibly private classifier on those features obtained from those classifiers on their local data, and we can reduce the error down to 5% from 25 with the same privacy guarantees. That's just one simple example. We have many, many methods implemented in this framework, but there is just not enough time to tell you about everything my group and my collaborators with me are doing. So we also devised and trained distributed neural network training and differentially private and, well, privacy preserving rather. Um, so and many many other models. So that's it. Thank you. And here's my group. People. Well, those are people who I advise or co-advise. All cool researchers, and most of this work and a lot of work that didn't make it into the stock was done by them, and they're working on even more interesting stuff. Just letting you know, we have a few positions. I have a few positions in the group available. Looking for a postdoctoral fellow for next 3 years, and can accommodate a couple of new PhD students. If you know someone interested, tell them to drop me a line. Thank you. Bye bye.